And as you progress down, things become increasingly more complicated. And it seems like implementing something like Ward's method would actually be pretty expensive, and it would be a lot more computationally difficult than something simple like the single link. It turns out that all the methods regarding of what notion of distance you use, they can be implemented as part of the same exact algorithm with the same computational complexity. And that's called the Lance-Williams algorithm. So it's the efficient algorithm for constructing a hierarchical clustering of the data points. The way it works is you start by estimating a pairwise distance matrix between the original points. So for every points xi and xj in my data, I'm going to compute a distance between them, maybe Euclidean distance, maybe some other distance if I think that's better, and store all of those distances in a big matrix that's going to be n by n. N is the total number of instances. And then what the algorithm is going to do is it's just going to do your normal iteration, and all the clever part is going to be in the updates. Right. So for n iterations, until I end up with just one cluster that captures everything, what I'm going to do is I'm going to look over the matrix Dij, and initially what that matrix represents the distance between the singletons, right, between the singleton clusters. So I'm going to look over Dij, I'm going to find a pair of closest clusters in there, and then I'm going to merge them, delete the clusters I and j from the matrix, and add the cluster I plus j. Right. So on this little example, on this little graph that I have three nodes, I, j, and k. I have the distances dij, dkj, and dki. So I'm finding, I'm looking for the minimum distance, right? So the smallest one is dij. So what I'm going to do is I'm going to merge I and j into a cluster I plus j. And then I remove that edge between I and j because they're part of the same cluster now. They don't need to be there. And what I need to do is I also need to update the links from all the other clusters to this newly created cluster. Why? Because previously there were two. There was a cluster I and cluster j, and k had distance to both of them, and now there's only one cluster. So I want to leave only one edge going from k to this new cluster I plus j. So what I'm going to do is for each remaining cluster k that was not I or j, I'm going to disconnect k from I and from j, and I'm going to connect it to I plus j. Now, with what distance am I going to connect it? If I was doing single link, it would be very easy. Right. If I'm doing single link, I'm going to be connecting k to the closest element of this new cluster, I plus j. So k would be just connected to j. So if I was doing single link, I would just take the min. I would look at how far is k from I, how far is k from j, take the smaller of the two values, and that would give me the distance between k and this new cluster I plus j. So for single link, it's very straightforward. Now it turns out that you can replace the simple operation, the minimum of two numbers, with this slightly more complicated expression. And for different setting of constants, you're going to be able to implement any of the distance metrics that we had on the previous slide. Okay? So let's look at that. It's a linear combination of a bunch of things. So let's look at what those things are. It's dki, so the distance between k and element I, dkj, so the two clusters that I merged in the previous step, k had distance to those clusters, so they're part of the formula. The distance between I and j themselves, right? And then the absolute value of the difference in the two distances, distance from k to I and distance from k to j. Right. This is a number, so I'm just taking the absolute distance between the two numbers. And what I have here is a bunch of constants, alpha I, alpha j, beta, and gamma. And it turns out that if you set those constants in different ways, this formula will reproduce different types of distance functions in the hierarchical clustering. So, for example, if you take if you set alpha I 2.5 and this should be alpha j 2.5 and beta to 0 and gamma to minus 0.5, you're going to end up with single link clustering. So that's going to be the same as the minimum. We're going to go over that example. But before we do that, let's do something simpler. Right? So let's take group average. Remember, group average, the distance between the two clusters, you take all the pairs going between them, you take all the distances, and you average them out. Okay? So why does this setting of constants work out for group average clustering? Okay. So I had my cluster K, right? I had my cluster I, and I had my cluster J. Now, what I've done is I've merged the I plus J. But let's look at what was there before. Right? Before that, I had the distance from K to I and the distance from K to J. Now, what was the distance from K to J? The distance from K to J was the sum over all pairs. So I had an element x in K and element x in J, and I looked at the distance between xk and x. It's horrible notation, but you understand what I mean. So I was looking at all the distances, all the pairwise distances between points in J and points in K. So that was dkj, normalized by the total number of those points. The total number of edges, sorry. And dki was the same picture for k and I. It was the average of all the links going between k and I. Now what happens when I merge I and j together into one cluster? These links, they don't change, right? The links going between k and my new cluster I plus j is just a combination of the links that were going to I and the links that were going to j. So all I need to do is I just need to add them. Right? If there was the same number of links here and here, I would just add them and divide by 2 to get the average. Now that's if there was the same number of links going from k to I and from k to j. There could be more elements in I than in j. In this case, the average from I should count more. So that's what those weights represent. It's the number of points in I divided by the number of points in I plus and j. So you're creating a weighted average. Because there's more points in I, you're going to assign more weights. You're going to assign more weight to dki. Okay? And then you're just combining dki and dkj. The other constants are 0. Okay? So what you can do is, if dki and dkj previously reflected accurate average distances between clusters k and I, then I simply combine them into one, and I get the distance from the new cluster I plus j to the old cluster k in one scalar operation. Okay, so that's for group average. That's very simple. Now let's do something a little bit more complicated. Let's do the single link. So what we want to do is we want to show that if we set alpha I, alpha j, and gamma to 0.5, gamma minus 0.5, then we're going to end up with just the single link rule. And remember, the single link rule was the minimum between the two distances. So that expression is going to work out to be the minimum. Let's see why that is the case. So if I plug in those constants, what I have is the new distance between cluster K and the clusters I plus J is 1/2 of the distance between K and I plus the distance between K and J minus the absolute value of the two distances. So the argument is, the argument sort of goes as follows. Out of these two numbers, dki and dkj, right? These are just two numbers. One of them is bigger than the other, right? So let's sort of arbitrarily say that dkj is the smaller one and dki is the bigger one. Okay? Now, the distance here, dki minus dkj, what I'm doing is I'm subtracting the smaller number from the bigger number, or the bigger number from the smaller number. It doesn't matter because I'm taking the absolute value, right? So I have this, I have a big number, dki, a small number, and I'm subtracting the difference between big and small. So I take the big number, I subtract from it the difference between the big and the small. What am I going to get? The small number, right? And now I have the small number plus another small number. So the result of that is going to be twice the small number. And when I take 1/2 of that, I'm going to end up with just the value of the small number. So what I get as a result of that is just the min, right? And that is a consequence of a general rule. You can convert maxes to mins by subtracting the absolute distance between the two numbers, right? Nothing magic. There's nothing complicated. You can do the same argument for complete linkage. Right? Very similar argument. Notice the only thing that's different is now this is 0.5 instead of minus 0.5. So now I have a big number, a small number, and I'm going to add the difference between the big and small. Small number plus the difference between big and small is the big number. So I have the big number plus the big number divided by 2, just the big number. Okay. So for complete link, these constants are going to give you the max of the two numbers. Okay. So you've got a nifty little rule that for different setting of constants is going to implement just about any notion of a distance metric that you can come up with.